we have one more part of the January 2024 New York State Chemistry Regents Exam to do, and this is it, Part C. Now, there's 4 parts to the exam. The first 2 parts, multiple choice. The last 2 parts are short answer questions, and Part C, again, is the end. We're going to go from 66 to 85. If you're watching this video, good for you. A lot of times when students study on their own, they only look at the multiple choice. But of course, short answer questions, just because you have to come up with the answer, are going to be more difficult. They're not impossible. There's a lot of repeats, but the answer is not in front of you. Anyway, with that, let's get started. For question 66, it says compare the number of protons to the number of electrons in an atom of oxygen 18. Now, these types of questions, you get these reading passages typically with a group of questions. Sometimes you need that information and sometimes you don't. When we're going to compare the number of protons to the number of electrons for oxygen 18, oxygen, of course, is the element. 18 is the mass number. Now, the number of protons is the atomic number. It is not the 18. The 18 is the number of protons and neutrons. These isotopes mean the number of neutrons vary, but not the number of electrons. Now, if you forgot the atomic number for oxygen, real simple, go to the periodic table. And here we are at the periodic table. Oxygen is element 8. 8 in this case is the number of protons, and 8 is the number of electrons. There were no charges with the oxygen, meaning it's neutral. Protons equal electrons. Now, with this question, it does say compare. They are equal, so just make sure that you don't forget to answer the question. Let's move on to 67. It says to go ahead and draw the electron dot diagram for an atom of oxygen. The electron dot diagram is going to show each dot as a valence electron. And while oxygen has 8 electrons total, when we look at the electron configuration, it's 2-6. 6 is the number of valence electrons, it's the outermost electrons. In our dot diagram, then we need 6 dots to represent those 6 electrons. Now, I have my symbol, and I'm going to go ahead and draw dots. Depending on what your teacher has told you, typically the first electrons in the valence shell or level are paired. So we would show 2 dots, that's 2 of the 6, then 3, 4, 5, and 6. Mine look kind of like dashes. But as long as you have 6 dots around the symbol, you're going to get credit for 67. And now 68, it says state in terms of. In terms of neutrons means you better have neutrons in your answer. You could give a correct statement, but not get credit. So why a water molecule containing oxygen 18 atom has a greater mass than a water molecule, which is oxygen 16. The greater mass comes in because there are 2 more neutrons for oxygen 18 than oxygen 16. We're checking out questions 69 through 71. We have a lot of information here. We have a table. We have a couple of equations. And then we have questions that come from all parts of the course. Starting with 69. It says show a numerical setup for calculating percent composition by mass of oxygen in sodium hydrogen carbonate. Well, you got to do a little digging here. It's not hard. Percent composition by mass, your percent is always the part, which in this case is the oxygen, over the whole thing, which is the gram formula mass for the sodium hydrogen carbonate, which is actually given to you already, and making sure you have it equal to percent, and that's it, because you're not calculating an answer, you're just showing the setup. Now, with the oxygen here, for sodium hydrogen carbonate. And by the way, if you didn't know, it's right here. You just have to read it in the passage. You have 3 oxygens for every 1 unit. So you're not going to just put in the gram formula mass for oxygen. You need to multiply it by 3. Where do you get that? Periodic table. Just want to mention on reference table T, here is that percent composition calculation. And of course, I forgot to mention it's times 100. When you do your setup, don't forget this. Here is oxygen again. Now, the gram formula mass for oxygen is the 15.9994. We're going to just round it to 16 and go back to the question. Here's my setup. My percent oxygen is going to be 3 times 16. You could even just put it as 3 times 16 or plug it in your calculator, and that is 48 over the 84. And again, don't forget, like I just did, times 100. That's what they're looking for. All right, let's check out question 70. Determine the number of moles of K2CO3 produced when 3.5 moles of KO2 completely reacts, represented in equation 1. So we're looking for moles and we're given moles. And we have a balanced equation, equation 1. This is what I call a mole-mole problem. It is just a ratio. The balanced equation is like your recipe, but now instead of following the coefficients in front, we're given 3.5 moles of KO2. Let me show you how I show my students an easy way to figure this out. We are going to put the information above the equation. So the 3.5 moles of KO2, 3.5, and our X is K2CO3. Underneath, put the coefficients. So we have a 4 here. For every 4 moles of KO2, 2 moles of K2CO3 is made. That's a 4:2 ratio, which is a 2:1. Now, if you still don't see the answer, it's okay. Just put a line and an equal sign, and sure enough, what do you have? You have a proportion. Now you're going to solve for X. If you don't know, you're just going to go ahead and multiply both sides by 2 and divide by 4 to get the answer. Then you're going to cross multiply and divide. It's as simple as that, right? So 3.5 times 2, which of course we know is 7, is equal to 4x. And now we want to get x alone. We're going to divide both sides by 4. Don't leave it in a fraction. Use your calculator. So 7 divided by 4, and our answer is 1.75 moles for 70. For question 71, we want to balance equation 2, and it tells us using the smallest whole number coefficients. What you're going to see in the answer booklet is exactly what you see up here for equation 2, but we're going to balance it right from here. What I tell my students, real simple, is just to move from left to right with the equation. In other words, I have 1 sodium right now on the left, and I have 2 on the right. I'm going to put a coefficient of 2. Now that coefficient goes for the sodium, the Na, the H, the C, and the O. Let's move on. Now I would wait and do hydrogen and oxygens last. Let's check out carbon. With the 2 in front here now, we have 2 carbons on the left. We have 1 plus 1 here on the right. We have 2. Then we're going to check out oxygen and then finally hydrogen. Right now, 2 times 3, right, we're distributing, is 6 on the left. On the right, I have 3 from the O3. I got a 1 and I got a 2, and that adds up to 6. And finally, if I do hydrogen, 2 on the left and 2 on the right, and it's balanced. So all I needed to do to balance this equation is to put a 2 in front of the NaHCO3. For questions 72 and 73, I have this reading passage, and then I have a graph. Make sure you check out the x and the y axis. On the y, we have volume in liters, and on the x, temperature in Kelvin. For 72, determine the volume of the sample of helium gas at 350 K. Well, let's take a look. If I look and find 350 and I want to determine the volume, I'm going to go up and then I'm going to go over. Sorry for my lousy lines here. All right, it looks like, let me erase this. It looks for the 350 line right here, essentially, and I'm going to go over. And now the only hard thing is figuring out, which isn't hard, what the individual boxes mean. It looks like for every box, we're up a half a liter. So we're above 5.5, but below 6. So we're going to be at 5.75 for the volume of this gas. I just checked the answer key, and they allowed a range of 5.6 to 5.9 as an answer. So you're going to be pretty good on this one. For 73, compare the average kinetic energy of helium atoms in a sample of 200 K to the average kinetic energy at 300 K. One of the things you want to remember walking into that exam is temperature is a measure of the average kinetic energy, in this case of helium atoms. If the temperature is going up, so is the average kinetic energy. And that's all you have to say, right? The average kinetic energy for the helium atoms at 300 Kelvin is higher than at 200 Kelvin. For questions 74 through 77, again, we have a reading passage along with a balanced equation. How do I know it's balanced? Well, I see the coefficients and energy is put in there as well. So for 74, explain in terms of collision theory why reacting hydrogen and nitrogen at high temperature increases the rate of reaction. Well, we just had gotten through the fact that temperature is a measure of average kinetic energy. Well, at high temperatures, we're going to have more collisions, and those collisions are also going to have more energy, which increases the rate of reaction. For 75, determine the net quantity of heat released when 1 mole of ammonia gas is produced by this reaction. Well, let's go to this balanced equation. These coefficients, remember, our ratio, our recipe. For 2 moles of ammonia, I get 91.8 kilojoules of energy coming out. They didn't ask about 2 moles. They asked about 1 mole. Again, I can set up a proportion. Clear this. Let's do this again. I'm looking at 1 mole. I want to figure out how much energy. Well, 2 moles gives me the 91.8. So again, what am I dealing with here? I'm dealing with a proportion. If it's half the number of moles, it's going to be half the energy. In other words, 2x is equal to 91.8, and 91.8 divided by 2. I'm literally putting it in the calculator. That is 45.9. And that's kilojoules. For 76, using the axes in your answer booklet, draw a potential energy diagram for the reaction. We're not going to go to the answer booklet. We're going to just do it right here. Move that up a little. Get my pen. What type of reaction do I have? Energy is a product. This is exothermic. In other words, we're starting at a higher energy and ending at a lower energy. And what's in between, right? We have that activation energy. So here is an example of an exothermic potential energy diagram. For 77, in terms of activation energy and reaction pathway, why the addition of a catalyst increases the rate of production of ammonia. What catalysts do, yes, they speed up the reaction. I'm going to change the color here. Let me make it blue. But what it does is the catalyst change the reaction pathway, which in turn lowers the activation energy, right? You had the reaction pathway and activation energy that have to be in the answer. Again, reaction pathway gets changed with the addition of a catalyst, which lowers the activation energy. All right, reading passage again. We have a reaction again. And 78, identify the element present in the reactants that allows them to be classified as organic compounds. Organic compounds have carbon. So carbon is the answer here. For 79, write a chemical name for reactant 1. All right, so reactant 1, you got carbons, you got hydrogens, and you have oxygens. Now it's important to note there are 2 carbons here. The 2 are oxygens. Let's go to reference table R. Reference table R gives us a list of what's called functional groups. These are elements other than just carbons and hydrogens that you would find on organic molecules. Remember, we're looking for 2 oxygen atoms. Sure enough, here it is. Reactant 1 is an organic acid. Now, it's not propanoic acid. That's the example they give us, but we can work off of that. Prop, if you look at the other organic reference table, tells me I got 3 carbons. I don't have 3 here. I have 2. The prefix for 2 is eth. The reactant is ethanoic acid. Just to recap, reactant 1, you have 2 oxygen atoms, which makes it an organic acid because you have the H at the end. For the functional group, you have 2 carbons. The prefix is eth. So this is ethanoic acid. For 80, write a formula for the missing product X in the equation. Well, of course, we're assuming everything is going to be balanced, right? We don't lose or gain any elements. They're just going ahead and they're getting rearranged. So we can figure out what is left over for our reactant X. Okay, so on the left-hand side, right now we have 1, 2, 3, we have 4 carbons. And on the right, we have 1, 2, 3, we have 4 carbons. So X is not going to have any carbons in it. Let's look at oxygens. We have 1, 2, 3 oxygens, but on the right-hand side, we only have 2. That means oxygen has got to be part of X. Now we're looking at hydrogens, and we have 2, 3, 4, 5, 6 hydrogens. And on the right-hand side, we have 3, 4, 5, 6, 7, 8 hydrogens. Does that make sense? Did I screw it up? I think I screwed it up. Let's back up. I think there's 8 hydrogens on the right. Let's check out the left again. There is a total of 4 hydrogens, and then 3 plus 2 plus 1. That's a total of 6. 6 plus 4 is 10. All right, so what are we missing? We're missing 2 hydrogens, and sure enough, it's H2O. Now, another way to recognize missing product X would be the classification of what reaction this is. You have an organic acid, and you have an alcohol. When they join, they form what's called an ester, and the other product is water. 81, identify the class of compounds to which the product belongs. Sure enough, the COO here in the middle is an ester. Now, what you would do is you go back to reference table R. You would find there's only 2 groups on there that have 2 oxygen atoms in the molecule, esters and organic acids. But organic acids, I can show you right here, right? Because this is one has an H at the end. Here, what you see is carbons and hydrogens on both ends. That makes it an ester. All right, we are finishing out Part C of the January 2024 Regents Exam with 82 through 85 nuclear chemistry questions. So 82, compare the penetrating power of a beta particle emitting from iodine-131 nuclide to the penetrating power of an alpha particle from uranium-238. Penetrating power of beta particles is greater than a penetrating power of an alpha particle. That's a fact, Jack. Beta particles, essentially, they're electrons being spit out of the nucleus, where an alpha particle is 2 protons and 2 neutrons. For 83, complete the nuclear equation in your answer booklet for the decay of iron 59 used to diagnose anemia disorders by writing the notation for the missing part. All right, here is the actual equation that was given in the answer booklet, and it's beta decay. So iron 59. What you do is you just go ahead and you balance the mass. Masses on both sides, they have to be equal, and the atomic numbers. So 59 is equal to 0 plus what number? 59. And then 26 is equal to a minus 1 plus. Now you got to be careful. It's minus 1, right? So it's 27 minus 1 is going to get you equal to 26. Don't put 25. A lot of students do that and they'll get it wrong. What we're looking for is the identity of element 27. Let's go to the periodic table. And sure enough, here it is, right smack dab in the middle. It is cobalt. So to finish this up, I'm going to go ahead and put the symbol for cobalt. So it's cobalt 59. For 84, you're asked to determine the fraction of the original sample of the radioactive isotope used to test for thyroid problems that remains unchanged, excuse me, I'm getting tired here, after 24.063 days. I go up to my table. We're talking about iodine-131. I got to go find the half-life. Let's go to the reference tables. All right, we're at reference table N. We need iodine-131, and here's the half-life, 8.021 days. Now, there's a couple of ways that we can get the fraction. Your teacher, I'm sure, showed you one way. Whatever you're comfortable with to getting the answer is going to be an eighth. Works for me. I'm going to show you 2 different ways. One would be you take the total time, which is the 24.063. We divide it by the half-life of 0.21, and we figure out the number of half-lives. So literally 24.063 divided by 8.021, and it's 3. What that means is, when I'm dealing with a fraction, so that you're going to deal with the whole thing, or number 1, then half-life goes by, you have half of the original sample, the other half has transformed, a half of a half now with the second half-life, and you have a quarter, and then half of a quarter, which is an eighth. And there's your answer. That's one way to do it. The other way that I show my students is just doing a table. It's essentially doing the same thing. Let's check that out. Okay, so we have 2 columns for the table. One is time and one is mass. A half-life goes by, and we're at 8 and change, at 8.063, but that's so close to 8, we're going to leave it at 8. And what do we have? We have half of the original sample. Another 8 goes by, 8 days, and that's a total of 16. And we have half of a half, which is a quarter. Then I add another 8 days to that. We get to our 24, which is an eighth. So what am I doing? I'm adding time as it goes on, and then I'm halving when I hit each half-life. No matter which way you do it, the answer for 84 is an eighth. You are definitely going to see a half-life problem on the test, probably at the end, just like this group of questions. Just practice, and you'll be fine. Finally, for 85, determine the number of neutrons right here in AM 241. Well, 241 is the number of neutrons and protons, we need to subtract the number of protons. Let's go to the periodic table and get the atomic number. All right, in order to find it, we got to go all the way down here. 95 is the atomic number. That's the number of protons. Let's go back. All right, and let's go ahead and subtract 95 and 241. I'm using my calculator. And the answer is 146. That ends Part C of the January 2024 Regents. I hope you got something out of this. Just keep working hard. The more questions you practice, both the short answer and the multiple choice, the better you're going to do. Check out more stuff on my channel. Again, work hard and good luck.